What was the first leap toward the Riemann hypothesis? It was the introduction of j of x, a new prime-counting function. Jx was defined as a function that counts not only primes, but also their powers with weights. But there was a big problem. Since Jx was only a definition, Riemann could compute it only by counting one by one. He couldn't fully grasp it. If Jx was to be studied precisely, it needed an explicit formula. Riemann had to find a way to express Jx in terms of something else. That's where the second leap appears. To move forward, he needed a completely new way of thinking, and mathematics already had one. There is a standard technique called partial summation. It looks complicated, but don't worry, we'll focus on the idea. The left-hand side is a series that depends on the choice of an and s. Now, look at the right-hand side. Zoomed out, it's just an integral, but inside the integral, we see the partial sum. So, this formula transforms a sum into an integral. But what does this have to do with j of x? Everything. Let's define an like this. If n is 2, 3, or 5, an equals 1. If n is 2 to the power 2 or 5 to the power 3, an equals 1/2 or 1/3. If n is 6, 10, or 12, an equals 0. Substitute an into this expression and then expand it. The left-hand side becomes this. What is this? This is log zeta of s. Now, look at the right-hand side again. The partial sum adds 1 for each prime and 1 over k for each prime power. This is exactly j of x, Riemann's prime-counting function. Suddenly, everything transforms like this. Look at this. This was the doorway to the second leap. Why? The zeta function can now be written as an integral of j of x. That means we can reverse the process. We can recover j of x from the zeta function itself. Still, one question remained. How can you recover j of x from log zeta of s itself? This is where Perron's formula enters the story. In simple terms, this formula extracts a counting function from a series. In our case, that series is log zeta of s. So, by applying Perron's formula to log zeta of s, Riemann was able to extract j of x itself. Wow! This was Riemann's second leap. Jx was no longer just a definition. It was now expressed through another function, the zeta function. And after analyzing this integral, Riemann realized Jx could be reconstructed from the traces left by its singularities. From those contributions, this explicit formula emerged. It consists of 4 terms in total. Each term comes from a singularity hidden inside the integral. Using this formula, Riemann could calculate j of x in a completely new way. Compare j of x with pi of x and li of x. Jx doesn't just describe the overall growth of primes. It captures even their fluctuations. In that sense, Riemann went even further than his teacher Gauss. All of this comes from a single connection between j of x and the zeta function. That's why we call this connection the second leap. Riemann also realized the behavior of primes was shaped by special complex numbers called non-trivial zeros. Riemann had arrived at the doorstep of the Riemann hypothesis. What are those special complex numbers? How can they control primes? That is the next story.